Hi, everyone. We'll get started. So I hope you can see my screen. I will be walking you through this problem. It's basically a sales prediction or a sales forecasting problem. The idea here is that we have this data set, which is basically sales data for around close to 1,600 products across 10 different stores across different cities. Now, the idea here will be that we have different attributes or features regarding items which have been sold or products which have been sold. And also we have details about the stores which are selling them. So the overall objective here is that can we build a predictive model and try and predict that for a particular product which is being sold at a particular store, what is going to be the total sales, basically. So every row of data basically consists of a particular product which has been sold in a particular store, and we also have the total sales for that item because it can be sold multiple times. So the idea is to find out that, okay, if I'm stocking a product, let's say I'm stocking a can of Coke, so people will come and buy these cans. So how many cans will sell? Or overall, what is the total amount which will be coming in the form of sales? That's the high-level objective. So if you see here, we'll now look at the overall objective from a machine learning perspective. So the idea is to find out or basically build a predictive model to predict the sales of each and every product being sold in specific stores. Now, given that we will be predicting the sales, it is ultimately going to be a regression problem if you think about it from a data science or a machine learning perspective. It's a regression problem because we'll be predicting the sales, which is a continuous valued number, which can range from 0 to a positive limit, let's say 20,000 or something. And since we already have labeled data, we can easily transform this into a regression problem, given that it's going to be supervised machine learning, where we will be training models at the end of the day to try and predict the sales. And before we train these models, we will go through a structured step-by-step process to first understand the features of the data we have, and then slowly head into the general steps of data loading, processing, EDA, feature engineering, and then trying to build some models. Okay, so if you look at the dataset details here, we have item identifier, which is going to be the unique product ID. Like I said, ultimately, we are trying to predict the sales of specific products being sold in stores. So there will be an item identifier column, which will basically give us a unique identifier for a particular item. Okay, we don't have the item name here. It's anonymized, but we have some kind of a unique identifier. We also have the weight of the item that will also be available to us. What's the overall weight of the item? We have other kind of statistics, like what's the fat content of the item, the visibility of the item type, maximum retail price. So all of these, if you see the first few columns, which we will be having in our data, are all related to attributes or features related to the items which are being sold. And the next columns are all related to the outlet, which is selling these items, which includes things like the outlet identifier. So again, this is anonymized. We don't know the name of the outlet, but we have a unique identifier saying that, okay, this is outlet A or B or C and so on. Okay, we'll have some identifier ID. We have the establishment year, which tells us when was this outlet opened, which year did it get started. And we have some other statistics or other attributes of outlets, like the size, the location type, the type of the outlet, and the final column, which is the column of our interest, is the target column, which is basically the sales, which basically will tell us that what is the total sales of this particular item when it is being sold in this particular store. So at the end of the day, once we train our model, assuming we have trained it on some data, the objective will be that given we have an item, its attributes, the outlet which is selling this item and its attributes, can we predict what will be the total sales for that item? Okay, so that's going to be the overall objective. I see some messages about the notebook. So the link has been shared in the chat above. You can check it out. If you don't see it in the messages, maybe someone can just paste the link and you can get the link. Okay, so to get the data set, I have already provided you the dataset link if you want to download it manually. The recommendation is to do it in Google Colab because you don't need to install any libraries, and that will save us time because then we can focus on the problem at hand. So I have also provided a link programmatically using which you can download the dataset directly into Colab. So let's start with that. First step is to download the dataset, which has been made available to us. So right now, as you see, there is no data here. So I will run this first step. If you want, you can code along with me. I will walk you through it anyway, step by step. If you feel I'm going too fast, just type it in the chat. And if you want, you can, of course, type along with me also. So this you'll already have it. All this is doing is it is getting a particular file ID from my Google Drive, and then it's basically downloading this data set, as you see, salesprediction.csv. So all our data will be in the CSV file. Okay. So next step, we will load up the data set. The easiest way to load the data set is to use pandas. Most of you might already be familiar with this library. So we will be importing pandas as PD, that's the alias. And then we will be using this command, pandas read CSV. And then you can put in the file name, which is sales_prediction.csv. Okay, and then you can run this cell. It'll take a bit of time, maybe, depending on the infrastructure of your system. If you're on Colab, it'll be pretty fast. So now our data set is loaded up. And our data set has been loaded up from a CSV format into a data frame format. Okay, so a data frame is nothing but a very similar data structure like an Excel spreadsheet, rows and columns. So let's look at our data. If we do df.head, we can see that we are able to see the first 5 rows of our data, starting from row number 0. And you can see the exact same column names here, like item identifier, which is the unique ID of the item weight, which is the weight of the item. Fat content is like whether it's a low fat or a regular fat or maybe more fat. We'll see the distinct values later on. For now, what you need to know is this basically tells us the fat content of the item being sold. Visibility can be a question that, okay, what does this number mean? So let's talk a bit about what does item visibility mean, because right now we are in the data understanding phase. So typically, if you're working in a company, you would go to the domain experts maybe and ask them that, okay, what does this column mean? Okay, so here we have this information available to us from the domain experts who have collected this data for us. So item visibility, if you see the description, it tells us that the percentage of the total display area of all products in a store which are allocated to a particular product. So hopefully that gives you an idea that, okay, if there are 10 products in a store and one product is getting, let's say 80% of the shelves in that store are stocked with that item, then the visibility will be 0.8. Because considering all possible items which are being sold in that store, 80% of the shelves in the store are being stocked with a single item, let's say. So that is basically the visibility, the percentage of the total display area. You can imagine that the total display area is 1 or 100%. So in that 100% or 1, how much is occupied by a particular item? So what this tells us is if the visibility of this is 0.016, this tells us that the item FDA15 is occupying around roughly 1.6% of the total store area, is stocked in total 1.6% of the store area. So imagine like you have multiple shelves in the store, roughly 1.6% of the shelves has been stocked with this item. Okay, so that is known as the item visibility. Item type, as the name suggests, it's the type of item, like whether it's a drink or some kind of meat or fruits, vegetables, and so on. Okay, so different categories of the type of item. Item MRP, as you know, MRP is the maximum retail price. So this is the item price in rupees for each and every item. Okay. So all these columns are related to the attributes or features of the items being sold. Next, we have the attributes or features of the outlet, which is selling them. So that's where we have the outlet identifier, which is a unique ID, identifying a particular outlet. Establishment here, as we suggested earlier, is basically the year this outlet was established, which means the year when the store started selling items, basically, the year the store opened, basically. Outlet size, as the name suggests, is the size of the outlet, whether it's a large size outlet or a medium size outlet and so on. Location type is basically what kind of a city is this outlet situated in, whether it's in a tier 1 city or a tier 2 city, tier 3 city, and so on. As you know, like different cities are grouped into these tiers. So this is based on like a tier 1 city might attract more customers, maybe because it's in an urban location, a lot of working people and so on. But doesn't mean that maybe tier 3 cities may not attract customers. There could be a lot of maybe grocery items and other items which are being sold. So it really depends on what the data tells us. Okay, we can have some assumptions, but we can't go with those assumptions unless we actually get some insights from the data. Outlet type is what kind of an outlet is it, whether it's a supermarket type 1, type 2, and so on, or a grocery store. Now, we don't have a lot of information about what the supermarket 1, 2 mean, but it can be, you can think of it as categories saying that maybe a size of the supermarket or a specific type of supermarket. Okay, that is the minimal information which we have at this point. And the last column, as you get it, it's basically your sales, which you have to predict that, okay, given all these attributes that, okay, I am selling item FDF15 with these attributes in store OUT 049, what is the total sales? That is what we'll have to predict once we train some model. Okay, so that's basically our objective at the end of the day. So now what we will do is we will go into the next step, which is preparing the data sets for training and then, of course, data cleaning and so on. So I see a question that how to identify the exact identifier key on which a model is to be built. Yeah, it is based on the business logic. Like in general, when we feed data into a model, we ideally shouldn't use identifiers directly unless we know, like in this case, we want to predict for a specific store or a specific item. So that is where we will use them then. Otherwise, it's mostly, yes, completely driven by the logic of your problem, where you have to decide, do I use all these features, or maybe some features are not useful to me, and so on. But typically when you're dealing with identifiers, it is totally based on your business problem. Like in this case, since we are specific about identifiers and like selling a particular item in a particular store and finding the total sales, we might need to consider them in general for different areas, or you will see in the feature engineering step to extract different features if necessary. Okay, so preparing, training, and test data sets. So let's talk about this. We will need data to train a model. Without data, we can't train a machine learning model. We all know that. We will need to train the model on some data, and then to measure the performance of that model, we need some unseen data. Now, we cannot wait for new data to arrive, obviously. So what we'll do is the existing data, we will split into two sets. 70% of the data we will use for training the model, and once the model is trained and we have our best model, we will evaluate the performance of the final best model. We'll come to that later on 30% of data, which was never used in the training process. And we set the seed to 42 just for reproducibility, so that when you split the data or when you train some models and so on, no matter how many times you run it, whether you run it now or after a year, you will keep getting the same results. So things will not keep changing. Okay, so first step is to figure out what are our features. Our features right now, we will consider everything as our features. Later on, we will drop things to experiment. When we are starting with, we will start with all our data as features. So everything will be a feature for us, which we will use to feed it into the model. except the sales. Why except the sales? Because that is what we are predicting. If we already know the sales, then there is no point in predicting the sales. We want to make the model learn the relationships between sales and all the other features. So all the other features are our input or our X, and we want to predict Y given X, and so our Y will be the sales. So that's what we do here. We do a df.drop item sales, which means drop the sales column and keep all the other columns. Okay, so that is our X, and our Y will be just the sales column, because we want to train a model to learn to predict the sales given all the other features. Okay, so we set that up first, and then we split our data using a train test split on our X and our Y. We keep the test set to 30%. And we set a random state just to ensure reproducibility, so that no matter how many times you run this, the exact same rows will be in the train, and the same rows, the other rows will be in the test. Okay, so now once we run this line, what you will see is, based on the shape, we have around close to 6,000 rows of data for our training and close to around 2,500 rows for our testing. So we will train our model on this, and later on we will check our model performance on this. Okay, I see a question, why 70-30? That is a standard in general, like a convention, but there is no one to tell you that that is what you should use. You can play around with that test size also. You can do 80-20, you can even do 90-10, maybe in some cases, if you are lacking training data and you want to train on as much data as possible. So you are free to experiment with this, but once you set something, like, don't keep changing it, is what I would say. Okay, so our X train, again, everything except the sales, because we are trying to predict the sales, and our Y train will be just the sales. So now, from now onwards, you will see that we will continue to build our analysis using only the training data. We will completely forget about the test data, and we will continue with only the training data. And that should answer your question about the data leakage. That is exactly the reason why we split the data right at the start, so that we don't end up getting information from the test data indirectly when we are training our model. Okay, so that is basically typically our data leakage, where one form of data leakage where we don't want to get information about unseen data into our analysis. So we will only consider the training data. And the next step for now is, again, this is not a super complex data set. So we are removing sales from the features because obviously we want to predict sales. But typically, another form of data leakage could be that you have some features which, if you already know, you can predict the outcome. So then you need to remove those. Like, you are predicting whether a person will not pay their loan, and you have a feature that this person has not paid the loan for the last 6 months. Maybe then you don't even need machine learning. If a person hasn't paid their loan for the last 6 months, chances are they are going to default on it. So those are the kind of other more complex data leakages which we may need to check and handle. So now we make a copy of our training data so that we can do some explorations, modifications, but we will not end up modifying the training data. Okay, so for all our modifications or basic experimentation, we just make a copy of our training data so that we can do whatever we want with this, but the original trained data will stay untouched, so that we can apply all the transformations together right at the end before machine learning. Okay, so we make a copy of our training data. Now we do an info, so dataframe.info. This tells us that in our training data, we have a total of 5,966 rows. We can see that some are of type object, some are of type float, and some are of type int, right? The data types. And interestingly, we can see that there are some columns or some features which are having less data, less non-null data, which means there are some null values present. Okay, so another quick way to see this is you can type data frame, which is xtrain c .isNull.sum. So isNull will return true or false. True is typically 1 and false is 0. So if you sum it up, you will get the count of the number of rows which are missing. So now if we run this cell, it tells us that item weight has around 1,000 rows missing. Outlet size has around 1,690 rows missing. Okay. We need to think of a way to handle this. Okay, we need to think of a way to handle these missing values. We are aware about this, but we'll come to it later on. So hold that thought. Let's start by doing some basic EDA. Okay, so we'll start with just the numeric features, which are item weight, visibility, MRP, and establishment year. All the establishment year is more of a discrete numeric value, more of a categorical. You can think of it in that way, but let's get into it. So a good way to separate your data to just get the numeric columns of your data frame is you can do data frame dot select d types, which stands for select data types, and you can say exclude equals object, which means show me all the columns of the data frame which are not of data type object, which means don't show me these object columns, show me the non-object columns, which in my case are the floats and the ints, the data types which are numeric in nature. Okay, so we run this cell now. And as you can see, it rightly shows us only the numeric features of our data. We can do a quick describe. The describe function will basically give us the basic statistics, and you can check the min and the max values quickly just to make sure that you don't have any negative values or some weird values, right? It's a good way to quickly check for outliers also. In this case, our data set is pretty robust in that way that you can see that the item weight is having some realistic values in this case. Although we have a fair number of rows of data missing, as you can see, the rest of them have the full data, which is non-null, but we have over 1,000 rows, which are missing or null, which we have to handle. And you can look at the different statistics like mean, median, okay, and then standard deviation and so on. This is the maximum retail price. So you can see that the minimum price here is 31, maximum is around 266 and so on. So we are able to see different values basically here. Okay, so now what we will do next is we will look at the is null again, just for the numeric features. This tells us that this is a numeric feature which we need to handle for the missing data. Now we just load some basic libraries here for visualization. One is Seaborn. It can help us in visualizing some data without writing tons of code, which we would have to do if we use matplotlib directly. We need matplotlib for some finer controls like doing subplots, splitting the plots, and so on. Okay, so we import these two libraries. And now we will visualize our numeric data. We can visualize these using histograms, univariate visualization. So we can do a histogram for weight. We can also visualize it as a box plot. So we do a figure AX equals PLT subplots. What this tells me is I will have one row of plots. Okay, I will have one row of plots, and I will have two columns where each column will host one subplot. So basically, I will have one big plot, and that will inside that there will be one big figure rather, and inside that there will be two subplots. The total size of the figure is 12,5. And then what we do is we put a hist plot here. So we do Seaborn hist plot. We put the data frame, and we put the name of the column which we want to visualize. In this case, we're visualizing item weight, and we use hist plot because we are trying to visualize it as a histogram. And you see this AX0. AX0 means in the first subplot of the figure, put the histogram. Okay, and then what we do is, in the second one, the Seaborn box plot, we plot the same data frame again and the same column of that data frame. And we say AX1, which means the second subplot should be a box plot. So that's why we use AX1. And this basically gives us this kind of a figure, which basically shows us that item weight distribution itself. overall, and it shows it as a box plot also. And box plot kind of tells us what is the 25th percentile, the median, 75th percentile. Not too many outliers if you think about it in that way. The data is more or less having overall kind of like a uniform kind of distribution, and it has different weights between 5 to 20 plus. Okay, so then what we can do is we can put this code into a reusable function, and that's what we do here. If you see, we define a function, def visualize numeric features. It takes as an input the data frame. It takes as an input a specific column name, which we can pass as an argument. And then what we can do is we put the same code here, which we had, literally into this function, except we parameterize these. That, okay, the data frame you pass as input, I will pass that to the hisplot function. I'll pass it to the boxplot function. The column name you will pass as an argument, I will pass it to the arguments here for plotting the distribution of that column. And then you can just call this function with the data frame name and the column name, and it'll show you the same thing because we have called the same column name here. Okay, so whenever you have to do like a repeated thing again and again, you can create a function, and then you can use it to call and basically check out the distributions. Okay, so the next step is doing the same thing for all the other columns, all the other numeric columns. So that is where we again call the same function here. We pass in the xtrain C, the training data frame, and in this case, we pass item visibility. And now we can see that this is what the item visibility looks like. It's more of a right skewed distribution. And the same thing shows up in the box plot here. But here we have items which have a high visibility. Does that mean we should remove them? Probably not, because they could be super useful for us, because high visibility items could indicate that they might sell more. So you shouldn't just blindly remove the outliers. You have to think about it from a domain perspective also. Okay, similarly, we do visualize numeric feature, pass in the training data and the MRP in this case. And now we can see that this is what the MRP looks like. More or less, it has different modes, like it is a multimodal distribution with different peaks. Similarly, if we do outlet establishment here, it shows us some distribution based on a histogram, but again, it's kind of a very weird distribution, because obviously year is more of a not a continuous, but more of a discrete numeric column. So a better option would be, for this column, you can use a count plot and plot the outlet establishment here, which would then tell you how many products were sold in specific years. Okay, so in that way, you can see the frequency of products being sold in different years. Okay, so now we'll get into categorical features. I see the chat now. If you want this notebook, I can share it with you. You can follow along meanwhile with the lecture. So, or if you want to run, you can also use this notebook. That is, I'll just paste it here. Let's see. Okay, so you can use this notebook if you want to run along with me also. But anyway, I'll walk through it step by step, so you can pay attention to the screen and should be good. Okay, so far we have just visualized the numeric data. Now what we'll do is we'll look at the categorical columns. So that's where we just do data frame, training data frame, select D types, include equals object, which means show me only the object columns. And as you can see, the object is basically the string or the categorical columns, which include the item identifier, fat content type, outlet identifier, size, location, outlet type. And we can, again, do a categorical features.describe. And that tells us the total number of rows for every feature. And we can clearly see that outlet size has some missing data, which we need to handle. It tells us the unique features for each of these columns. And this can be a very good way to quickly check if there are some categorical features which are high cardinality categorical features, which means they have a lot of categories, basically. They have a lot of distinct categories. And as expected, item identifier has a bunch of unique categories because every item identifier is like a separate product. And obviously, a lot of products will be sold in any store. So this is something which basically tells us that something to watch out for, that you may end up having too many features. So we may need to think of some way to handle this later on. Top is basically the mode value, the most frequently occurring value in each of the columns. If you want to look at the mode, you can. It's not super useful always, but sometimes you may want to do data imputation using mode for categorical data. So then it's useful, but there are more sophisticated methods, which can be using machine learning itself, using something like k-nearest neighbors, or using domain knowledge, which is what we will do in our session today. So now the categorical features.isNull.sum, this basically tells us that all the columns are more or less good in our training data. The outlet size is something which is something to watch out for. Next thing we can do for EDA for categorical data is obviously frequencies. What is the frequency of the different categories for specific categorical columns? So we can do categorical features, item identifier value counts. This shows us the number of rows of data for each category in item identifier column. And this tells me there are 9 rows of data for this product, same for this product, and so on. So we can see there are many products which have been sold in only one store. They have not been sold in multiple stores. Similarly, now we can look at the unique values of item fat content. And as soon as we do value counts, we can see there are some inconsistencies in our data set where low fat has been mentioned in different ways. One is in title case, one is in abbreviation format, and one is in lowercase. So we may need to handle this and make it more consistent, standardize this. Same thing with the regular fat content. We see that reg and regular both kind of mean the same thing. So you need to merge them into a same categorical string ultimately, because otherwise, if you encode these and feed it to a model, the model may think they are different categories. So we need to make these consistent even before we go into feature engineering or encoding. We'll come to this shortly. Next thing, we look at the item type, number of rows, or the frequency of each item type category, and we see that there are different item types as expected. We have fruits, snacks, household items, and so on, okay, dairy, and so on. And these show the total number of rows of data, or the frequency for each of these categories for item type. Similarly, outlet identifier, this tells us that there are a total of around 10 stores which are selling products. Outlet size, we have medium, small, and high. Outlet location, we have tier 1 cities, tier 2 cities, and tier 3 cities. So those are the categories which we have. We don't have city name available. We just have the tier. That's it. And outlet type, we have supermarket type 1, grocery store type 3, and type 2. And this shows kind of the frequency of the number of rows of our transactional data for each type of outlet. So next step, we will do some data wrangling and feature engineering now, which includes both the pre-processing and cleaning our data also as necessary, because both will sometimes go hand in hand. I will answer some of these questions now. So let's see. I think we have answered the 70-30, 80-20 thing. Notebook link, I think I've shared in the chat. Hopefully all of you have got it. Do we have any method to check if the trained population distribution and the test distribution are same or different? There are different ways to do this. One option, and this is something which is there in ML Ops also. So you have distribution analysis where you could plot the histograms of your training and your live data coming in the future and compare the distributions visually. There are statistical statistical metrics also, like you could do a correlation of training feature versus test feature, the same feature, and they should be ideally highly correlated. You can do a KS test also, which is often used to compare distributions. Okay, you can use a KL divergence also to compare distributions. So there are different metrics and statistical formula which you can use to compare them at the end of the day. Okay, and based on some values which you get as results, based on looking at those visuals, you can say that my live data is maybe drifting away, right? That's one of the common themes in MLOps, data drift, where your live data or the future data, the features are kind of changing over time. So these are some tests you can use to kind of check those. We won't be covering all of that today, given the session is focused more on just a structured approach to this, but those are some things you can check out for the future. How to incorporate learnings from EDA and feature creation. Honestly, it depends on what you're doing. So this is a very generic question. Trends and so on depends on the nature of your data set. Okay, so we can maybe, if there are specific questions, we can discuss on that. But the idea is from EDA, you get some insights about specific values. Then you decide maybe you need to create a completely new feature, or you need to derive some existing, you need to derive it from multiple features maybe. So it's more of a domain thing. You could use statistical things like mean, median, and other things, but you should be careful about those. When building the final model, is it better to use the entire data? Yes, you can use the entire data when you're building the final model before you go for deployment. But once you train your final model on the full data, you can no longer, again, use a test data from it. Okay, so when you're going for deployment, you can take your best model configuration, train it on the whole data if you have lack of data, and then deploy it. But then you have to wait for new data again if you want to do some evaluation. Okay, so we'll get going again, given the time at hand. So now data wrangling and feature engineering. So first step is a basic feature engineering, which we want to do is, as we discussed, the item identifier, we have a lot of items. Okay, so we could use every item identifier as a feature, but what we'll try to do is we will try to create some more generic features, okay, instead of relying on specific item IDs. We'll talk about the item IDs also later on, which we can use as a feature, given that this problem is focused more on per item prediction. But if you look at this, every item, you will see that we have some FDs, we have some NCs, and we have some DRs. So if you talk to the domain experts, imagine you are working with this company who has provided you the data. They come back to you and tell you that FD means food items. Let's say DR means like drink items, and NC is like non-consumable items, right? Like general items which you can buy and use, but they are not for eating or consumption, okay? Like a pen maybe, and so on. So what we do is we create a high-level feature. And what the idea for that would be is to take the item identifier. Let me run these quickly, by the way, since we are running this live. Just run it from here. Okay, so if we see, let me show this to you. Excuse me. So this is our item identifier column. We can do an apply like this. And what this tells me is for every row of the data, that's X, that's denoted by X, show me only the first two characters. Okay, so that's what it does. So if you run this now, you will see that it shows you just the first two characters. And then we do a value count just to see that, okay, there are over 4,200 sale transactions of food items, non-consumables around 1,000, and drink is around 560. So we can use this as a high-level categorical feature. Now, if you see carefully, I have used a different way of doing the same thing also. So the reason for this is just to show you that there are different ways in which you can achieve the same thing. Okay, so there are different ways in which you can get to the same results. Usually, if you're working on larger data sets, often you will see that apply function takes a bit more time to compute. So if you can get a simpler transformation, you can use that. Like, again, just to quickly show you, you have xtrain here. Now, these are strings, okay? These are actually strings. So you can use a .str to access them as strings. Okay, so you can use a .str to access them as strings and then use a specific method. Like a string is a list of characters, so you can slice it. And you can tell it that slice every row and show me just or get me the first two characters. So that's another way in which you can do the same thing. Go with what you feel comfortable with, but when you think about performance in the future, maybe just be careful with functions like apply. Okay, so now we know that this is a way to get this new column. So what we'll do is we'll create a reusable function, because the exact same sequence of steps which we apply on the training data, we want to apply the same sequence of steps also on the test data. So that is what we do here. We want to map the item ID into an item type. We want to create a higher level item type feature from the item identifier. So that is where we create a function, def create item type. The input to that function will be a data frame. Then what we do is we extract the first two characters of the item identifier for every row in the item type column. In the item identifier column, we extract the first two characters for every row in the item identifier column. And then what we do is we assign it to a new column and we call it item type. And then we transform these names into something more meaningful. For machine learning, it's not useful because machines don't care about meaning, but this is just to make it more understandable for us at the end of the day. So what we do is we use a map function, and in this map function, we transform FD into food, NC into non-consumables, and DR into drink. So all this is doing is for every row of our item identifier, like FD and 08, it will extract FD, and then it will convert this FD into food, basically, and put that into a new column. Okay, so we create this reusable function, and then we apply it to our xtrain C, just to see that whether it's working or not. So we do xtrain C equal to create item type xtrain C, which means it takes in the training data as input into this function, it creates a new column, and then it returns back the data frame, and we store it back to the same variable. You can store it to a different variable also, but we just keep the same variable again. And as soon as we do it, you can see that we end up getting this new column called item type. So anything starting with FD becomes food, NC becomes non-consumables, and DR will become drink, basically. Okay, next step, we have to handle missing data for item weight, because if you remember, item weight has a bunch of NaN values. Okay, so just to recap, item weight has some null values, we have to handle that. So what can we do here? One insight is, do we have the same item being sold across different stores maybe, and for some transactions, the weight information is available, but for some transactions, the weight information is maybe not available. So a quick way to do that is to just do training data, item identifier, item weight, drop duplicates, and then sort the result by the item identifier. So as soon as we run this, it will show me all the unique rows consisting of unique values in item identifier and weight. And if you see the result of this closely, you will see that item identifier is the same here, but drop duplicates doesn't remove this because we have different values in the second column. So if you see this carefully, what this tells me is in some stores, the item DRA59 is being sold where the weight information is available, but in some stores maybe, or even in the same store at a certain date, maybe for some reason it was not available, maybe a data entry issue or something. So the idea here is if we know the item ID and we have some historical mapping, which tells us that, okay, this item has this weight, why not use this information itself to fill in this value, basically. Okay, so that is exactly what we will be doing. We will be creating a mapping between item ID, item identifier, and item weight. So that whenever we get any data frame, we will look at the item weight column. If it is missing, we will go into the dictionary. We will find the value for a particular key, and then we will fill this with this value. That is the logic we want to use. Okay, so that's what we will do. Now, we also want to do something else. Now, if you think about this, this is very specific to item ID. So your question could be that on the test data, or even let's say on live data in the future when your model is deployed, what if we have some kind of an item ID which is completely new, right? Or which was never there in the training data? How do we fill it in, right? So because maybe we created this mapping, but there is a new product, DRA 1000, and that was never there in the training data, which means we would never have a mapping of weight to that item. So we can follow different approaches here. What we will do here is just a simple conditional mean approach that if for some reason our mapping dictionary of item identifier and weight, we don't have the item ID present for which we want to fill in the missing value for the weight, what we do is we take the median weight of food items and we store it. We take the median weight for items of the drink category, and we take the median weight for items of the non-consumable category. And then what we can do is, if for some reason there is a completely new product and for some reason we don't have its weight, we just fill it with the median value based on the item type. Okay, so that is the second level of missing data imputation for the item weight column. First level is if you have a mapping based on item ID and weight, use that to fill it in. For some reason, if that fails because the training data never had that item, look at the item type and then take the average, not average, but median weight of that item type and use that to fill it in. So that's what we do here. We look at all possible drink items, all possible non-consumable items, all possible food items. We take their weights and we compute a median value. So now we will put this logic, which I just explained to you, inside a function. Okay. So if you look at this function here, we want to fill in the missing values for item weight. What is the logic? The first step is build a mapping of item ID and weight so that in case the weight is missing for a product, you use the item ID and then you use the non-null weight to fill it in. If for some reason it is a completely new item that its item ID was never seen before in the training data, use an item type and take the median weight of that item type and fill in the missing values. Is it the best approach? It's one of the good approaches where you're using a conditional operation. You could do other things also, like use a machine learning model, use something like k-nearest neighbors, but here we are going with a slightly simpler approach. So first step is to create this mapping dictionary of item ID to weight. So how we do that is we first build a pivot table, okay, which will give us item ID to weight. In case you want to see how this looks like, this is what we create first. So for every item ID, we will have a corresponding weight, every unique item ID. Okay, the pivot table helps us to get the item weight for each and every item ID. And all we do next is we take these two columns and we take this data frame and we convert it into a dictionary. Okay, so that is where we use a dictionary between these two columns. And this is what a dictionary looks like. I've used items here, so you see it as a list of tuples, but this is a dictionary. So DRA 12, the weight is this, DRA 24, the weight is this, and so on. So in case in the future we have DRA 12 coming in and the weight is missing, we will fill it with 11.6. Next step is in case this fails, the item is completely new, we use this. Okay, so we take the item weight, we compute the median value of the item weight for each unique item type. Okay, so for drink, we will fill it with 11.8. If it's food, we'll fill it with 12.8. If it's non-consumable, we fill it with 13.05. And now we put in our reusable function, impute the item weight inside the data frame, where we update the item weight column of this data frame. The first logic is use the item ID. So we use the fill NA function to fill all the NA values or the NaN values in the item weight column. And how do we do that? We look at the item ID and we use a map function using this dictionary, which means look at the item ID. If there is a match, take this value, put it in this fill NA, which will fill in the NaN value for that particular row. Now, if some data is still missing, look at the weight, use a fill NA. Fill NA will only affect rows which are having NaN values. So if something was filled in this step, it will not be replaced in the second step or the second logic. Okay. So here we fill it with the item type weight mapping. So now we can test it on our training data. Again, same way, pass in the data frame to this function. And you can now, oh, I didn't run this, my bad. Run this. Okay, so now if we do isNull.sum, we see that the item weight is completely filled in. Now we need to think of filling in the item, we need to think of filling in the missing values for outlet size. So for outlet size, what we have to do is we look at some basic statistics. Again, we'll use domain knowledge in this case. So what we do is we group by outlet type and outlet size. And what this tells us, if you see that in our data, if the outlet type is grocery store, most of the time, or almost all the times, the outlet size is small. Now, if the supermarket type is 1 for that particular outlet, out of all the transactions, 1,312 of them, the outlet size is small. So this is the only case where we have contradicting categories for outlet size. So what we can do to resolve that conflict is choose a simple approach that go with the most frequent value and use small. So all we are trying to do here is use a conditional mode instead of a global mode value, that if it's grocery store, it will be small, no conflicts. If we know that the outlet type is supermarket type 1 and the outlet size is missing, we use the mode of this and we fill it with small. If the supermarket type is 2 and the outlet size is missing, there are no conflicts again. We fill it with medium. We don't need to take any mode in this case. We already know it's medium. Similarly, if the supermarket type is 3, we fill it with medium. Okay, so all we do is we import the mode function. We do a pivot table of outlet size and outlet type. If you want to look at this result here, I will quickly show this to you. So all this is doing is it is computing a pivot table between the outlet size and the outlet type, and it's using the mode. So when you run this, you will see that, sorry, need to import this. So when I run this, you will see that for grocery store, it will fill it using small because there is no conflict here. It's always small. For supermarket type 1, there are some conflicts. It uses the mode to give us small. So whenever it will see that the outlet type is supermarket type 1, it will fill it with small. Type 2, it will fill with medium. Type 3, it will fill with medium. And all we do in this cell now is to convert it from a data frame into a dictionary. That's pretty much it. Okay, if you want to look at the raw value of this variable, it's literally a dictionary. That's it. Now we define a reusable function to fill in the missing data. So impute outlet size, pass in the data frame, update the outlet size, where you do a fill NA, and you do the fill NA, and you use a mapping function here. And you can see that you fill it with outlet type size mapping. So what that means is for any rows where the outlet size is a NaN, it's missing, look up the outlet type for that row of data, use this dictionary, and based on this, you fill in the missing value. Okay, so now we call it on our training data. And now, as you can see, all the missing values have been dealt with. Okay. Now there are some other things where we have to standardize item fat content categories, because what we had seen before is that there are some values where the low fat, there is LF, there is low fat in lowercase, and so on. So it's very simple here. We just need to use a basic mapping where we take that column, item fat content, and wherever it is low fat, we make it as low underscore fat. Wherever it is LF, we make it as low underscore fat. Wherever it is REG, we make it as regular. And wherever it is low fat, we make it as low underscore fat. Okay, so all we are doing is we are keeping regular as regular. Wherever it is REG, we make it as regular. And wherever it has different variations of low fat, we are just standardizing it to a single category, low underscore fat. That's pretty much it. So now when we call this function on our training data, we can see that we no longer have all these different inconsistent categories. We have low fat and regular. Okay, that's pretty much it. Now let's look at a bit more. Let's get a bit deeper into the domain aspects of it, because when you're creating some of these features, or rather correcting some of these features, you have to be very careful in terms of the meaning and the significance. Okay, so if we do a group by on our training data based on item type and the fat content, and we look at the number of rows, we get this insight that there are 517 transactions for drink where the drink was a low fat drink, which makes sense. There are drinks available which are low fat drinks, like healthy drinks. We see there are some drinks which have been sold which are regular drinks. Around 43 transactions have been done. Similarly, for food, you have healthy, like low fat food, which is being sold. You have regular food also, which is being sold. But interestingly, for non-consumables, the fat content has also been put as low fat. Now, as you know, non-consumables are basically products like maybe a pen or whatever, right? A writing pad and so on. So there is nothing of a notion of a fat content being there. Okay, so if the model is to learn the right patterns, it needs to understand that consumables are the things which will have some kind of a fat content, but non-consumables cannot have low fat, right? So all the rows of data for non-consumables, the item fat content, we need to change this. Okay, it can't be the same as low fat for food or drink, okay? It has to be something else. We have to correct that. So that is where we create a basic reusable function again, where it will check for all the rows of data where item type is non-consumables, take the fat content column and set it to non-edible, which makes sense because there is no fat content, it is non-edible. You can name it any value, but whatever you name it, you can just keep it consistent, don't keep it changing. So now when we call this function on our data, we see that it's all good now. Okay, we have the correct information so that the model learns the right things, because otherwise it's garbage in, garbage out. It may end up learning some wrong patterns. So now this is our data set, our training data. As you can see, it looks pretty decent. So now we will create a reusable function which you can use at any point of time on any data set, be it training, be it validation, be it test, be it some live data coming in the future, and it will be very useful whenever you are deploying a model. So all we do, if you see, is we create a function called prepare dataset. It'll take as input a data frame. Then literally the functions I created in those steps, step 1, step 2, 3, 4, 5, we are just calling those functions and modifying the data frame one step at a time. That is all. And the best part is you can call this on any data frame and it'll work. Okay, so now let's look at our actual training and test data, if you remember. So our training data here has these nulls. All we do is very simple, one line of code, xtrain, prepare dataset xtrain. Nulls have been handled. Similarly, xtest, we have a bunch of nulls. Same way we handle it, xtest prepare dataset. Okay. Now we could handle categorical data and also put it into these functions and so on for the feature encoding or the engineering for the categorical data, but we do it separately just to show you there are different ways of engineering categorical features. Okay, so let's look at our categorical data. A baseline model could be take a one-hot encoding or dummy variables and for each categorical column, which means every item identifier will occupy a column, fat content, every category will occupy a column, which will be either 1 or 0, right? So that is known as a one-hot encoding or dummy variables. So that's a first, a slightly naive approach. We do an import one-hot encoder. Any unknown categories in the test or future data will be ignored because the training data never saw it. So we set it to ignore. And we fit it on our categorical data. Then we get the feature names using these column names. We get the feature names, which is basically, as you can see, like every item ID becomes a single category. Similarly, every outlet type, every item type, they will become one column, basically, or one feature, which will be filled with 1 or 0. Okay. Now, our numeric data is basically this. So all we do now is we take our categorical data, we transform our categorical data of our training data set into one-hot encoded columns. This is what it looks like. Okay. We have a lot of features. The main reason for having so many features of our categorical data is because we are one-hot encoding the item ID also. Okay. So we have every item ID as one column. Plus, we have other categorical features like the grocery store, outlet type, outlet location, and so on. Okay, one-hot encoded or dummy variables. Our final training data will be our numeric data concatenated with the one-hot encoded training data, categorical data. Okay, so this is our final training features. We store the final columns just so our test data also, we will order the columns in the same way, basically. Okay, so that the order of the columns going into the model is always the same, no matter what data you're passing. So for our test, it is very straightforward. You separate your categorical data for the test. Separate the numeric data for the test, separate the categorical data for the test, transform using one-hot encoder the categorical features for the test data, convert it to a data frame, because by default, one-hot encoder converts it into a NumPy array. Okay, and then concatenate it, and your test data is also all good to go. Number of columns is 1573 in both training and test. So now what we will do is we will basically, if you look at the Y train here, Y train is the sales we are predicting. And obviously sales is a skewed distribution. We have a lot of items which are being sold with price between 0 to 2,000 rupees. And we have some items which are being sold, which are like high value items, but maybe people will not buy it as much. Okay, so this gives us a range of values in terms of sales. Typically, it's between 0 to around 12 to 14,000 rupees. So now we could start with simple models like linear regression, then go to nearest neighbors, decision tree, and so on. But given that this is more showing you like a step-by-step approach, we keep it very simple here, and we just go to tree-based models. We use some ensemble models here, like random forest, gradient boosting, as well as a new model, which is there in scikit-learn, called histogram gradient boosting, which can automatically handle categorical data natively without doing one-hot encoding. But you can one-hot encode and also pass it. Okay, you can also pass dummy variables. We will also try extreme gradient boosting, XGBoost, and LightGBM, which is LightGBM, the regressor variant, because we want to do regression. So we create a reusable function here. If you see, I'm not touching the test data anywhere. I will take only the training data. I will take a model, which I want to train and evaluate the performance. I will do by default 5-fold cross-validation using the cross-validate function. And what I will do is I will try to score the notebook. I will try to score this each model in this notebook by trying to show that what is the performance of each model, which I will be running in this notebook after this. And I will score the model performance using R-square and the mean squared error, root mean square error, RMSE. Now, because scikit-learn doesn't have root mean square error directly in the cross-validate function, it has negative root mean square error, so we need to convert it back to a positive value. So what I'll do is I will take my training data, I will split it into 5 equal parts. That is known as 5 folds. I will train it 5 times on 4 folds and then check the performance on 1 fold of the training data. I'm not involving the test data anywhere at all. And then I will print the model. I will get the test R-square. By test here, by the way, don't get fooled. Like, test is not the test data. This is the cross-validation score on the training data itself. And I will show that what is the score, what is the R-square of the model on each fold of the training data, what is the R-square of the model, the average R-square, and what is the standard deviation. Lower the standard deviation, the better it is. Similarly, I will get the root mean squared error. I will multiply by -1 to convert it from a negative value to a positive value. And then again, the same thing. I will show the root mean square error across each of the 5 folds of my training data. And I will show what is the average error of the model, average RMSE, and the standard deviation. So with this reusable function, what we can do is we can pass in multiple models one after the other, the same training data, and check the performance. Okay, so we run these models. It will take a bit of time to run, excuse me, because if you think about it, we are training on 1,500 plus features, which is a huge amount. Okay, so training these baseline models initially will take some time because first of all, we have a lot of features. And secondly, we are training using ensemble models like random forest gradient boosting, which by default uses 100 decision trees to come to the final decision. But you can increase the number of trees also. We are not focusing on tuning today. The focus here is just to benchmark the default configuration of some models and see that if you change some of these features, can you get a better performance? Okay, so that's something we will look at now. While this completes running, I will address some questions here. So, okay, Colab notebook, hopefully you have it. When to use the, should we not do EDA for the whole data? Okay, a lot of questions I can see. So outlier treatment methods, you can use a box plot, you can use the interquartile range. You can also, but the data, if the data is not normally distributed, you can look at other models, like you have mean, median absolute deviation. You can look at isolation forest. So there are different ways in which you can handle outliers. So you can play around with some of these methods depending on the nature of your data. If you have multiple features, you can use some machine learning methods like isolation forest. Should we not do EDA for the whole data? No. So we should only do the test data is like, you can imagine it's like live data which is coming in. So you have no idea about it till your model is deployed. So if you put yourself in that mindset, you will imagine that you don't have the test data. And that is why we created this reusable function so that no matter what your data is, you will process it in the exact same way you did when you trained your model. When to use mean and median? Honestly, this is something you can look at the EDA and decide. In most cases, you can go with mean if your data is more or less normally distributed, but otherwise you can also try out median, especially for skewed data. Correlation between categorical and numeric features. There is Spearman's rank correlation. You can look at chi-square analysis between categorical features if you want to. You can look at decision tree-based scoring methods also, like Gini and so on, to see which features are highly affecting a target variable or another feature. That is usually a better method than just linear correlation. Okay. Yeah, exactly. We pass the test data to the prepare dataset function to apply exactly the same methods which you applied on the training data so that it's consistent. What about missing values in the test data? We handled it, right? So if you remember earlier, we used the exact same steps. So we call this function, which will handle it in these two functions. So when you pass the test data here, this will handle it for you. Okay, so is label encoder a better option? Maybe if your data is ordinal in nature, like let's say you have something like size, you could label encode it, right? You could do 0, 1, 2. Outlet location type, maybe you could try label encoder. But for some of these other things like outlet identifier or item type, you can't do label encoder. So, and even item identifier, the one which has the largest number of categories. Okay, so label encoder, you can actually experiment with for columns which have ordinal data, some kind of order in it. Okay, so now let's quickly check our results. So you can see that the random forest model, the average R square is 0.54. The RMSE is around 1160 rupees. Okay, standard deviation 30.9. So not bad, but we can clearly see that the gradient boosting model has given us a far better result. A histogram gradient boosting result is better than random forest, but not as good as the vanilla gradient boosting model. Extreme gradient boosting model, XGBoost, has given us the best results so far. Okay, if you compare this. Okay, even the standard deviation is lower. Okay, if you look at it, which means that the chance of overfitting of this model is lower than the other models. Okay, light GBM scores look to be pretty high. Okay, so higher error is not good, right? So this is like on an average, you can make a mistake of 1,000 rupees when you're predicting something, given that you have so many high priced items. So the idea is how low can you make this number and how high you can make this number. Now, there are some models like Light GBM, even XGBoost, though XGBoost is experimental and it only works on a GPU, so we won't use it here. But histogram gradient boosting and Light GBM can handle categorical data natively without doing one-hot encoding. So that is where we, before we do that, what we do is we want to see that do we really need so many features? Do we really need so many features? What if we just drop the item ID? What if we just drop the item ID because we anyway have the high level item type, and what kind of a model performance do we get? Okay, so that is where now we take all our categorical data, but we don't include the item identifier. Okay, so our numeric columns are fat content type, item type, outlet identifier, size, location type, and the numeric columns are the weight, the minimum retail price, and all that. So now what we do is we compute the, this is the native handling. So we'll talk about this. So we compute the number of categorical columns and we compute the number of numeric columns. And we also have to convert the categorical columns into type category, because if you remember earlier, they were of type object. If you remember here, let me, excuse me, if you remember, these were of type object. So if you want to use models like Light GBM or histogram gradient boosting regressor, which can natively handle the categorical data, where you will pass it directly as strings, though in histogram gradient boosting, you need to still convert it to 0, 1, 2. You will need to convert the data type into category. So that is what we do here. If I scroll down again, I will convert all the categorical columns. Each of these categorical columns, I will convert it into the type, data type will be category. And numeric columns stay as it is. So you can see that they are categories and we have some numbers. So these are our features. You can see there is no one-hot encoding, which I have done here. Next step, what we do is we build a mask. What does this mask do? This mask just gives the signal to the model, to the histogram gradient boosting regressor model that, okay, these are my categorical features. The first 6 features are categorical. The next 4 features are numeric. it needs to give a signal to the model so that the model can transform the categorical features. And then we build a pipeline. The reason for building the pipeline is we need to convert every categorical column into an ordinal. Ordinal means if the categories are A, B, C, it will convert it into 0, 1, 2. Doesn't mean that it is taking an order, because when we will pass it to the histogram gradient boosting regressor, it will use strategies like frequency binning and other sophisticated methods to basically, as you can see, it has bins. It has a column called, it has an argument called bin. So it will use some strategies to handle categorical data natively. But we need to convert the categories to numbers before we pass it to this model. But for light GBM, you don't have this restriction. So that is why this pipeline here, all it is doing is it will take every categorical column and it will convert it to numbers, basically. And then we will pass the categorical data, which has been converted to numbers, along with the other numeric data, which is untouched, into the histogram gradient boosting. So if you see here, nowhere I'm doing any one-hot encoding, okay? I'm using the native data directly. And I have dropped the item ID, okay, because the model was taking too long to train, plus we had like over 1,500 features or categories, which is doesn't make sense to have so many. So now you can see that the overall score is 1142 is the error, and the R-square is 0.557, not as good if you think about it. If you train the light GBM model now, you can see it trains pretty fast. Within seconds, it gives us the result, and it is also no better. So what this tells you is sometimes you may need to do the transformations yourself. The models may not be able to even natively give you that good a performance, or basically, it's not like magically the performance will improve. So what we will do next is we will consider the same categorical data which we had. We will not consider the item ID, and we will do the one-hot encoding, just like we did earlier. Okay, so what we do now is we take this categorical data, we drop the item identifier because we don't want it. For the remaining categorical features, we do a one-hot encoding. So again, just to recap, if I run this again, .head, we will be doing a one-hot encoding of all these columns. And we keep the numeric features as it is. We don't touch it. You could scale if you want to, but for tree-based models, usually you don't need to scale the data. And then we concatenate the one-hot encoded and the categorical features, numeric features. So this is what it looks like. Okay, numeric features, and then you have the categorical features. And if you see, the number of features is much less now. Earlier, you had 1,573 features. Now you have only 30 features. So it's like from 1,500 features or 1,500 plus features, you have only 30 features now. So let's rebuild the model. We will try gradient boosting. If you see, nowhere I have touched the test data. Okay, all I'm involving is only the training data right now to get to the best model. We try all those 4 models again. So now if you see here, if you compare these 4 models, you can clearly see that the extreme gradient boosting model and the gradient boosting. In fact, the extreme gradient boosting model gives us the highest R-square, 0.59, and the RMSE is 1,098. So if we compare this with the earlier one, where we had all the features, if you remember, we had 1,573 features. If we compare the performance of XGBoost here, you can see that I'll just copy this so that we can compare it. So I will just paste it here. So if we see here, XGBoost regressor with 30 features only gives us 59 point. It has actually improved, if you see, from before. Okay, this one has decreased, which is good. Our overall error has decreased a bit, and our R square has increased slightly, which is good. We dropped so many features of item ID and we are still getting a pretty good performance. So this gives us a good idea that we don't really need to include item ID, at least in a one-hot encoded format. Okay, so that is one thing. Now, the next thing is the last part of this session where we just show you a slightly advanced approach that what if I still want to include item ID in some format, because here ultimately we are dealing with specific products, but we somehow want to do some kind of intelligent feature reduction. So one option could be you can try to do some PCA analysis, but typically PCA you have to do on usually all the features, right? So that it can capture the maximum correlations and then it creates each principal component. So one option is, if some of you know from NLP, there is something known as a word embedding, where you embed the meaning of a word into a fixed size vector. Here we will kind of do the same thing, except we are not using a neural network to train it. We use a mathematical function. Just like you have a SHA hash function, we'll use a hash function to convert every category of item ID into a fixed sized vector. Okay, so there is an interesting capability called feature hashing, which we will use from scikit-learn. The hash vector size, you can play around with it. Okay, so what we will do is we will represent every item identifier by a vector of 50 numbers instead of having thousands of features. Okay, one-hot encoding. So what we do is we call feature hashing and we transform our training data for just the item ID. That's it. The rest of the categorical columns are still one-hot encoded. We just transform the item identifier into a hashed vector, basically. So if you see the result of this, what's happening is, I just want to show you the first 5 rows of Xtrain. So if you look at okay, so the first 5 columns, the first 5 rows of the item identifier column are these. So each item identifier, instead of having every item ID as a column, we are converting every category into a vector of 50 numbers here. Okay, and it's using a hash function to compute this. The hash function, in this case, it's a variant of a murmur hash function, but you can use different types of hash functions in general. If you want to play around with it, you can even build your own feature hashing technique, okay? Like in cryptography and so on, you have actually, like network security, you have these hash functions which are used to hash passwords and other things. We are basically using a similar thing to hash every category into a vector. So what that means is now we have only 50 features to represent every item ID instead of having like a one-hot encoded thousands of features. Okay, so the rest of the columns remain the same, which is the 30 features which we had. Okay, just the item ID is now added as a vector of 50 numbers. So that is what we do here now. And this is what our final data frame looks like. Okay, so the one-hot encoder has been applied on all the categorical columns of Xtrain except the item identifier. We concatenate it with the numeric features without touching it. And now we add this new hash data frame, which is the hashed variant of the item identifier. And this is our final feature set. Okay, one-hot encoded features for the others, hashed features for the item ID, and then the numeric features. So now if I look at the shape of this, we will have around close to 80 plus features instead of 30. Okay, so we have around 80 features now. So now we build a model, gradient boosting and extreme gradient boosting, because those are the models which have been giving us the highest performance. So we don't train the other models now. And if we see here, in fact, the gradient boosting has gone down from 1100 to 1099. So it has actually reduced. And you see there is a huge, well, not a huge, but still a fair amount of reduction from earlier. So earlier when we didn't include the item ID, and we built this model, we got a score of this. Let me paste it here. So this was the result without item ID in any form and all the other features only. And this is using the item ID in a vectorized format. And you can see that the R square has increased and the overall RMSE has decreased. Okay, so all we do now is we pick this as our best model for now. And we create our test data in the exact same format. Okay, so we take our hash function, we transform the item IDs of the test data. We take our other object columns, other categorical columns. We convert it into the one-hot encoded vectors. We take the numeric columns and we keep it as it is. And we combine them all together. So X-test final also has 80 features. It should have 80 features. Okay. And then we train our model finally on the training data. Remember, we haven't tuned the model. So if you tune the model, it'll probably improve a bit more in performance. We fit it on the training data, the final training data. We get the predictions of the test data. And then we finally get the prediction performance on the test data. So you can see the R square is kind of consistent with what you got on the cross-validation. On the test also, you get a similar score, and the overall RMSE is 1056. And you can plot the feature importance if you want for the XGBoost model, and it tells us that things like the item maximum retail price, the weight, the visibility, which makes sense, obviously, that the price of an item is very important in determining the overall sales. Usually, visibility of the item, obviously, if the item has more visibility, it's better. Higher weightage items are probably the non-consumable products, which may have a higher cost. Okay, grocery stores look to have a very good sales, which could be because people buy a lot of grocery products. And looks like also you get other features also, as you can see here, like outlet type, some of the hashed features, and so on. Okay, so overall, this kind of brings us to the end, given that we are also out of time here. But can we do more with this? Yes, we can do a lot more. We can go ahead and try out hashing in other columns. We can, as some of you suggested, we can also not just do one hot encoding everywhere, but maybe try a label encoding for things like location type and outlet size, because these are ordinal categorical data. For the others, we have to do one hot encoding, or maybe target level encoding, target mean encoding, weight of evidence, different types of feature engineering techniques can be used, especially for categorical data. Okay, so that pretty much brings an end to today's session, given that also we are out of time. Hopefully this gives you a decent idea in terms of how you look at the data, focus on the domain knowledge, also the domain of the problem, split your data initially always, focus on the training data, do all your evaluations only on the training data, in this case using cross-validation. If you have a training and a validation data set, that is also okay. But don't involve the test data at all until the very end, because if you involve it at any stage, then you are kind of leading to the data leakage thing, where the test itself becomes indirectly part of the training process. Okay, so that is pretty much it. I will kind of answer the questions now before we wrap up. So if the cardinality is very high, is there any better approach? So hopefully that gives you an answer. I will type it again. Feature hashing is one technique. Okay, what else? We have weight of evidence. You can look at that. We have target mean encoding. Okay, you can even use, sorry about this. You can even use on embeddings, use neural networks to generate embedding representations of categories. Okay, so a lot of different approaches out there in general. Okay, label encoding also useful for if categorical feature is ordinal, example size, which is like small, medium, large. Then you can do label encoding. Happily, you can do label encoding. Okay, so those are some approaches in general. Creating these many columns is advisable, 1500 plus? No, as you saw in this case, it's not advisable unless there is a very good reason why you need so many columns. Okay, as soon as you start having a lot of columns, it becomes very difficult, one, to train. Second, if there are too many categorical columns like that, your model feature importances also get affected. And as we saw, there are better approaches to represent categorical data. Can we use transformation for skewed data? You could. So you can iteratively do these things, like you build these baseline models like I did, don't involve the test data, have functions like this, and transform your numeric data maybe, right? And then see if it helps. If it improves your cross-validation score, then yeah, you can go for it. Also think of the domain knowledge, like whether that kind of a transformation is okay or not. Okay, ideal scenarios to transform the data, log SQRT. The previous question itself answers that. So if your data is highly skewed, you can look at some kind of log transforms and so on in general. How can we trace the hashed item ID back to the non-hashed item? I think it is possible. Like if we check the documentation of this, there should be an inverse transform for sure. Ideally, it should be there. So then you can use that function in general. Yeah, looks like it's not there. But what you can do is, one option is you do the transformation and then you create a dictionary, right? For every category, you have the vector, and then you can just do like a cosine similarity of the vector, and usually it's 100%, or you just match all the elements, do a vector matching, and then you do a reverse. Ideally, there should be an inverse transform function, but looks like they don't have it. So you'd have to manually maintain a mapping. Okay, can we use an ANN for training? Yeah, you can use a dense neural network, artificial neural network for training. Even if you don't have enough data, there is no harm in trying it out because it's an artificial neural network. The quality of data also matters, so you can definitely use it. Can we use a voting classifier or a stacked model? Exactly. So here we didn't go into such advanced concepts because this was more of a beginner focused session, but you can do all of that. You can combine even multiple ensemble models together and do a voting classifier. You can get the output predictions of multiple models as a first level, put it into another model and build a stacked model. So yeah, all of these things you can do. Okay, so that brings an end to the session. I will pause for a moment in case there are any more questions. Feel free to ask in the chat. Oh, I see a bunch in the question and answer tab, so let me answer them. Does knowing probability distributions help in visualizing? Yeah, exactly, because then you can easily identify that, okay, this is probably an exponential kind of a distribution or a uniform or a normal. So knowing it definitely helps. Could you share the input data set? It is there in the notebook, which was shared with all of you. So you should have it there. The first cell in that notebook should have it. What if there is a value in the test data that is not there in the training data? So as you saw here, I will say it again, that we will completely ignore that. So we will ignore any values which are there in the test data, which was never seen in the training data. That means you are losing some valuable information. And that is why we have MLOps coming up. Well, I mean, honestly, MLOps was there since ages, just that now people are branding it and publicizing it. But when you are deploying models to production, you have to keep updating them. You have to keep retraining your model. So then the future data, you have to again retrain with existing data. And then those new categories will get incorporated as features. But till that retraining process is not done, they will be ignored because it was never seen in the training data. You have to keep the model unbiased. Okay, so yeah. We will get the file for practice. I think the file is already shared. They will share the notebook. I'll share this notebook. I will share the notebook link again in case anyone doesn't have it. Let me. So sharing the link in the chat again one final time in case anyone doesn't have it. Okay, this is the link. How to decide whether to impute mean, mode, or median? Mode is easy. Mode is when you have categorical data. Mean or median, I think we discussed this question that if you have a lot of skewed data, maybe median is a safe choice. Otherwise, you can go with mean usually. When do we use target encoding? We discussed if your categorical data has a high cardinality features, a lot of categories, you can try some target encoding then. What difference will it make if we do data cleaning in overall data set and divide results into train and test? Data leakage. So as we discussed just now, that if you did this one hot encoding on the whole data set and then you split it into train and test, it could be that there are some products which are only supposed to be in the test data but was never seen in the training data, but your model will somehow get to know it because that will come as features. Okay, let's say you are doing standard scaling, which we didn't do here because we're building tree-based models. So when you are scaling your data, if you scale on the whole data, it is learning the mean and the standard deviation of the whole data, and then it is scaling the feature values. So if you split after that, then it's like your training data is also being scaled based on what it's learning from the test data. Okay, so data leakage starts happening. So that is why always split your data beforehand. When you're working on some toy data sets, it's okay, it will not make a huge difference. But if you want to get into the real world industry mindset, always split your data beforehand. Okay, can we do transformations for skewed data? I think we answered this. Definitely you can do it. Is ID relevant for the model? To an extent, it is relevant for this model. How did we reduce dimensions? You saw one option is feature hashing, and I've talked about a bunch of other methods you can always check out. How to address multicollinearity here? You can look at correlations between numeric features. You can look at a chi-square test between categorical features if needed, but we don't care about multicollinearity here because we didn't use, we are going with tree-based models. So doesn't matter there usually. Okay, data set is in the notebook itself. How model is deployed in cloud and production, that is a pretty heavy topic, but what you can do is once your model is trained, like the XGBoost model, you can save this model on the disk. You can use a framework like Flask or maybe Fast API, and then you build an API which can accept some new input data, load your model. Not just load your model, use those functions. You remember we built those reusable functions. So use those functions to transform your data into the right format. And then you load your model, make the predictions, and then you store the predictions somewhere. Maybe you store it in a database, maybe you pass it to a front end and you show the prediction. Okay, so that is the high level workflow of model deployment. Now you can follow the same workflow and deploy it on a server in the cloud, like an EC2 instance. You can Dockerize your API using Docker, make a container and deploy it. So it's like you don't need to install a bunch of libraries all the time. Everything should be in the Docker container and the Docker file when you build the image. There are other approaches also, serverless and so on. But standard approaches are save your model, build some Python scripts to handle the data transformation, build an API on top of it to make the predictions, deploy the API. Okay, more things can be discussed, but today's session, it will be a bit too much. But yeah, that's pretty much it in general. Anything else? Good book for NLP, you can check out. I mean, I do have a book on NLP, but it's been a while, so you can just go to my GitHub. I'll share my GitHub with you quickly. This is my GitHub. You can go to repositories. Okay, and you can check out some of the NLP workshops I have done. I have a book called Text Analytics with Python. You can check the GitHub code for the second edition. That will be good. The book is a bit dated, so there are some newer books in O'Reilly for NLP. You can check those out. I would recommend doing some of those Stanford courses also, like Deep Learning for NLP or Basic NLP. Other than that, You can also check out the Coursera courses on NLP. They are also pretty decent. Okay, have you tried TabNet? Not on this data set, but you can try TabNet. That is also a pretty nice neural network architecture, which claims to work well on tabular data. So you can always try and see if it beats XGBoost. That could be a nice exercise for you. Okay, last 1 minute to answer questions. After that, we'll be ending the session. Can we group items using clustering? You could group items using clustering. That could be an option, but then you have to use all the other features and then group them. And then you use the cluster ID maybe as a category, right? So yeah, that could be an interesting approach. You could do that. How to handle hashed features for single data? You just need to do hash.transform. Again, this is not a neural network model. It's not learning anything. So it is just using a hash function to transform the category into a vector. So you just do the vectorizer.transform or the hasher.transform on any data, be it train, test, some live data. It will compute it using a hash function. Okay, already answered that. Good book to follow for ML. Honestly, I mean, I will let all of you decide or be the best judges, but there are a bunch hands-on ML using for scikit-learn or something, right? Hands-on ML, scikit-learn, and TensorFlow. Go for the 2nd edition. Okay, it's an O'Reilly book. 100-page ML book is good by Andre. But it's a bit theoretical. If you want to dive into the concepts, you can check out Intro to Statistical Learning. It's a heavy book, but it's a nice book to learn concepts. The newest edition, probably 2nd edition or 3rd, I forget. Go with always the latest edition. Okay, those are the ones I will suggest in general. Other than that, you can check out videos or courses on Coursera and so on. Okay, my GitHub link, if you're interested, I will share it here. Feel free to check it out as needed. Okay, so that is it from my side, I think. Hopefully it was a useful session. Again, we didn't cover everything, but we at least tried to cover most of the things, right? So in that way, hopefully it was useful. It was a beginner focused session, so we tried to cover as much as possible. So we can do an advanced session in the future also based on the interests, and anyway, Analytics Vidya is arranging a bunch of webinars, so look out for the future sessions. Okay, so yeah, I think that's all from my side, folks.